These are the lesson 1.1 part 2 activities. So we're supposed to read the description of a situation and then find a differential equation that models the situation, identify what each variable represents and give possible units, and if your differential equation contains an unknown constant, like a constant of proportionality, for example, determine whether that constant will be positive or negative. Okay, so when the electromotive force, or EMF, is removed from a circuit containing inductance and resistance by no capacitors, the rate of decrease of current is proportional to the current. So here's the great thing about being a mathematician. I have no idea what any of that means. I'm just going to focus in on the mathematical terms. Rate of decrease of the current. So the current is some kind of variable, like that's a thing that's changing, is proportional to the current. Okay, so let's let C equal the amount of current. I have no idea what units are for the current of an electromotive force. I'm not going to give it units because I just don't know. So the rate at which that changes would be dc dt is proportional to the current, some constant of proportionality times the current. And they told us that this is decreasing, dc dt, the rate of decrease. So this is decreasing, which means that k has to be negative to make the derivative negative. Or we could write it as dc dt equals negative kc, where k is positive. Either way, you have to make sure that the derivative is negative. The population of rabbits grows at a rate proportional to the number of rabbits. So that's just the Malthusian model. So we'll use R for rabbits. Or maybe P. I'll use P for population. The population grows, so its rate of change grows at a rate proportional to the number of rabbits. Oops, that should be P. Proportional to the population. Meanwhile, 35 of the rabbits are sold each month, so just minus 35. So it's not 35t, which is a common mistake. You would have to put a t in there if you were writing a formula for p, population at time t, because then you would do 35 each month times the number of months t, but this is the rate of change population per month, right? Number of rabbits per month. So my units here on dp dt is rabbits per month, which is already the units on the 35. So it doesn't need another t. And then we should note that k should be positive because the population is growing. Okay, the population of rabbits grows logistically with growth rate of k equals 0.2 and carrying capacity 1600 and declines at a rate of 20 rabbits per month. So the logistic model, if you remember, it says dp dt. It's the Malthusian model when the population is small, so it's going to be k times p. And then there's this other factor for when the population gets larger, 1 minus the population over the carrying capacity. So I'm just going to plug into this Malthusian model, although I should adjust it for this. And then, and declines at a rate of 20 rabbits per month, so minus an additional 20. Now I'm just going to plug stuff in. So dp dt equals, the growth rate of k is 0.2, so I'm going to put a 0.2 in for k. Minus p over the carrying capacity, which is 1600, minus 20. Okay, the rate at which a hot potato cools is proportional to the difference between the temperature of the potato and the temperature of the room, which is 69 degrees Fahrenheit. Okay, so let's let capital T be temp and little t be time. I wouldn't always you noticed earlier, I didn't define my variables in all of these, but sometimes, like for this one, it's confusing because there's two different kinds of T. So I'm just going to take the time to write down what they mean. So the rate at which a hot potato cools. So the rate at which its temperature is changing would be dt dt. Is equals proportional to, so there's a constant of proportionality, the difference between the temperature of the potato, so that's capital T, and the temperature of the room, which is 69 degrees. And the potato is cooling, which means its temperature is decreasing, so K is negative. Okay, the rate at which ice is formed on the surface of a lake is inversely proportional to the thickness of the ice. So the rate at which ice is formed, we'll call that di dt, the rate at which the ice is growing, thickening, forming, is inversely proportional to. So that means instead of directly proportional to is K times, and inversely proportional is K over. So inversely proportional to K over I. And K will be positive because it's growing. So you need di dt to be positive. Okay, find the equilibrium solutions of this differential equation. So remember, equilibrium solutions happen. The definition of an equilibrium solution is a y of t equals a constant. If it's a population, it's called in equilibrium. Like the population is not growing or shrinking, it's in equilibrium, it's constant. So if y of t is a constant, that means dy dt is 0, right? The population is not changing in size, so its derivative is 0. So here's my dy dt, this formula right here. I'm going to set it equal to 0. The only way a fraction can equal 0 is if its numerator is 0. So I'm just not even bothering with the denominator here. Now I have two factors equal to 0. So either t squared minus 1 equals 0 or y squared minus 2 equals 0. Here I get t equals plus or minus 1, and here I get y equals plus or minus square root 2. Now remember, an equilibrium solution looks like this. Y of t equals a constant. The solution to a differential equation is a function y of t. So that means that this t equals plus or minus 1 is not an equilibrium solution, right? It's not a y of t. So y equals plus or minus root 2, those are my equilibrium solutions. Okay, we have two different predator-prey models here. X represents prey and Y represents predators. In which system does the prey, X, reproduce more quickly when there are no predators? So if there are no predators, Y is 0, and there are equal numbers of prey. Okay, so dx dt for system 1, because they're asking about the prey, the rate at which the prey reproduce. So I only need to look at dx dt when there are 0 predators. So if you put in a 0 for y right here, you just get dx dt equals 5x. And in system 2, the prey equation, when you make the y 0, just gives you x. So assuming equal numbers of prey, system 1 reproduces more quickly, right? Because of the 5, the constant of proportionality is larger, so system 1. In which system are the predators more successful at catching prey? In other words, if the number of predators and prey are equal for the two systems, in which system do the predators have a greater effect on the rate of change of the prey? So we're looking at the rate of change of the prey. Okay. So I want to look at the prey equation in each of the systems. Okay, so now in which of these systems, oops, I forgot the X there, do the predators have a greater effect on the rate of change? So the predators are Y. So the XY interaction term, just want to look at that. Which one has a larger effect on the rate of change? And that would be in system 2 because the magnitude of the coefficient is larger. So it's going to have assuming X and Y are the same values in both systems, then that -8 is going to mean that the interaction term has a larger effect on the rate of change of the prey. So system 2 is the answer here. Which system required more prey for the predators to achieve a given growth rate? Okay, so we're looking at the predator's growth rate. So in each system, I want to look at dy dt. Okay, so they both have the same constant of proportionality, ignoring the interaction term. So they're both dy dt equals -2y. And then the interaction term tells you how the rate of change changes based on interaction with prey. So in the first system, we have 1/2 xy. So every time the predators and prey interact, we model that with an xy term, and it has a coefficient of 1/2. In the other system, interaction seems to benefit the population growth rate more because of the 6xy. Okay, so we're looking at the interaction term. Interaction benefits system 2 predators more, which means that system 1 requires more interaction to achieve a given growth rate. Its coefficient is only 1/2, so it needs xy itself to be bigger to create a bigger change on dy dt. So system 1 requires more prey, that is more interactions between predator and prey, to create a given growth rate.